Good. Okay, so welcome to the fifth lecture. Now, officially, welcome to the fifth lecture on privacy preserving NLP. And we finished somewhere last time, kind of unfinished, but with the open question. So, and I'm gonna finish it or repeat and to see how can we solve this issue. So, but just to remember what we talked about last time. One of the definition, we ended up with finally defining differential privacy. And here's again just the definition, what it means that we have something which is a mechanism working on a database and it's outputting some value. We are talking about counting things, so this would be some real numbers. And we say that this D and D prime were neighboring data sets, so they differ in one person, right? One removed, one edit. And we said like, well, the probability distributions over these two different data sets are, they differ by this factor, which is x to epsilon, e to epsilon. So do you remember what this epsilon was? How did we call that? Say again? No. It has a name, this epsilon. It has a name. It's a privacy budget, exactly. Yes. So this privacy budget bounds the odds ratio. Okay, so this is one of the definition, and if we have this algorithm, we have to prove that basically this holds for any neighboring data set and any output in our mechanism. So the first, what we had, at the first example, we are basically counting persons in a database with a certain attribute. So it was like the drug use, yes and no, and we proved that if you use Laplace distribution, if you draw from Laplace distribution with a certain scale, which was proportional to this privacy budget, so the B scale was 1 over epsilon, that you could basically preserve privacy or kind of fulfill the definition of differential privacy. And then, so there was the counting query. So we did this, even like with a formal proof in a way, which you might have done by your own or just kind of, we had everything we need to prove it. And then we turned it into real value query, and I guess the example was, what was the example again? There was a bank, right? We had a bank, and we're interested in not like how many people have certain attribute in the database, but maybe the sum query. So how many people together, I think we have the example here. So it was the real value query, which the output is basically a real number. So far, so good. So yeah, exactly. So this is the working example from last time. So we had this 4 people in the bank, and they are account holders when each of them have some certain debt in euros because they were buying a house or something like that. So Elise bought a house in Frankfurt West End, right? And our query was, what is the total debt in euros of all of these people? And as we knew that just reporting the raw number, the sum, would basically reveal or not protect privacy of anyone in the database. So because of outliers and because you cannot trust the other people if you're in the database or not. So we said, like, let's try naively use the Laplace mechanism for counting queries. So remember, this was our approach, but it failed, as we'll see later, or we saw in the last slide, last lecture. It failed for one reason. I mean, it was maybe not a bad idea, but there was missing something. So what is this? This is a counting query Laplace mechanism where we say, okay, draw a random value from a Laplace distribution scaled by 1 over epsilon, and then add it to the true value of this query. So it was for the counting. Okay, and then we will ensure that the differential privacy will hold for this sum query. No, of course not, and we saw why in the last example. Okay, so I'm just kind of recalling from the last thing. So where we had an example of two data sets or databases, D and D prime, differing in presence or absence of this first A. So this is in D we had A, and in D prime we removed Elise. And of course, Elise here is less like it's sort of like outlier. So the value is really high as compared to the others. So she has there's no way to hide in the crowd because the crowd is small. It's like just 4 persons in the database. So for the sum of the true value for the full database for D would be 2 million something, and when we remove Elise, it was much smaller. So now tried and failed was that, okay, yeah, let's use the Laplace mechanism with scale. Scale is 1 over epsilon, which is basically here and here and here and here. And let's see how far we can get with this. And we see like, no, we cannot get basically anywhere. Well, somewhere, yes, but for some large y's, y values, it will fail. So it doesn't hold this notion of differential privacy. So we basically break it here. So, and the question we finished last lecture is how to fix that. And maybe you had some thoughts about it, maybe not, but maybe you can think about it again now. So how should we fix that? I mean, how can we make sure that this will kind of not exceed 1? Maybe the Laplace distribution is not a bad idea in the first place, but maybe we're missing something. Okay, and now think about it. So we controlling the scale of the Laplace distribution. Excuse me. The scale controls the spread of the Laplace distribution. So if the scale is larger, we have more spread, more almost uniform distributions, which means the two distributions being in two different points will kind of tend to look similar as we kind of stretch the distributions. So the scale is a thing here. So we use the scale for the strength of the privacy for the epsilon, but maybe the scale is somehow also important for some properties of the database themselves. So maybe if we scale it better now, we can fix that. I mean, how can you make sure that this will be smaller than 1? How would you fix this? Very naively, the first thing that comes to your mind, how to fix that this is smaller than 1 for any y.
I tried the normalization for this.
Yeah, you would just divide by something.
And it significantly comes close to 1.
Well, okay. So normalizing is a key here, and I would say maybe even like very naively, if I just divide it by this number, so I just divide it by 2, 8 something, so it will be a fraction, then it will hold. It will be smaller. So this is just by dividing. So I'm basically making this smaller. Oh, is it just a hack or is it a property of this mechanism? We will see later. Okay, so this is good approach, like normalizing basically a thing, and we will see it. It's a property of the task or of the domain, and it's bring us to the notion of so-called global L1 sensitivity. Okay, so we'll come to that exactly in the next slide, what it means. So the question here we have to ask, how the potentially different neighboring data sets, how do they influence the output? Okay, so we had this example of, let's say, we use D for the full data set now. And here we have D prime as by removing LEs. Okay, so we have B for Bob, C, Charlie, and X for Xander. And okay, so what is this? What is this symbol? This ugly thing. Everybody knows that? Yeah, really? Everybody knows that? Okay, so it's a set difference. You can write like D minus A, or very fancy mathematically, which is the same thing. So it's basically you remove one element from the set. Okay, so it's a set minus. I'm using that for just make sure it's like two sets kind of. Okay, so we remove one element from the set and from the data set, and we model it here as a set because it's convenient. So we have B, C, and X. So the true value, now let's do this. Okay, so the sum of everything here is 2, 8, 07, 7, so all these ugly numbers. And I have to apologize, I made these numbers up and they're kind of really clumsy and really bad to work with. So we have to stick with them as a running example, but I'll fix that in next year. I'm gonna fix that to something like nicer, but let's stick to these numbers. These are kind of real numbers. So the true value, the full sum would be, the full depth in my bank would be 207, and so basically everything summed up. And if I remove A, so it will be D prime, I just sum up 7001.56. Okay, so this is it. What is the difference now of these two potential outputs? Oh, yeah, well, what is it? This is basically the value of Elise, right? Yeah, okay, cool. So this is 20 something, something, something. So this is one example of two neighboring data sets. What could be the other neighboring data sets? So now let D prime be D minus B. So we just remove Bob from the data set. And again, the true value of D is everything summed up. And after removing Bob, I get the other number, and the difference, oh, is again going to be the value actually of Bob. So now you should see the pattern now. Okay, everybody sees the pattern. Like what is the influence of every person in the data set on the output of the query, and on the query on two different neighboring data sets. This is very important. Okay, so now, well, we see that basically each person influences the query by some maximum value, right? In our case, in our data set, the maximum difference of those would be, let me just summarize it here. So these are all four options when I remove either Elise, Bob, Charlie, or Sander, and the difference. So the maximum difference here would be just the maximum value in the database, right? Because if I remove one person, I'm just getting the maximum value removed. So each person can change the result of the query by its value. Okay, so this is not surprising, but if we see it like that, it kind of reveals the underlying mechanism. So can we use this max value, this sort of max value, which is now kind of, this max value is determined by this very particular data set. It would be different for maybe another data set or another bank, so to say. For this particular bank, this max value would actually fix our problem. And so this is again, recalling the previous attempt. So we use this naive kind of Laplace 1 over epsilon scale, and this will exceed. So how to make the term smaller, this term smaller than 1 is exactly by using this max value and by dividing, this by the max value. So again, how to make the term, this term smaller than 1. So remember now, and you should have done the proof of this, the triangle inequality for absolute values. So this is the inequality we're gonna use. So okay, so these two, the difference of these two absolute values is smaller than the absolute value of the difference. So let's just plug it in and do a little bit of algebraic operations here. So so this is going to be A, and this is going to be B, right? So this is how I'm gonna use the inequality. So this should be smaller than the difference, the absolute value of the difference. So okay, now I'm getting rid of y here. I do the subtraction, and this holds. Oh, by the way, this is the Elise value again. This is the maximum value. Okay, cool. And now to make it smaller than 1, I just divide by this maximum value. Okay, so this is the trick, just sort of normalization, but this will ensure differential privacy in there. So this is cool. So let's plug this back, and here we fix that by dividing by the max value. Oh, this will hold. Now we now guarantee differential privacy. What did we do? We kind of scaled something and normalized something, which corresponds to scaling the Laplace value, as we will see later. So by scaling the Laplace distribution, now proportionally to the difference, we achieve privacy. So for this particular database, D and D prime only right now. But we can try to generalize. Okay, any questions so far? Is it clear what we're doing right now? We need to make this bounded by e to epsilon. And we used wrong scale maybe for the counting query because we don't have a counting query, we have some numeric query. So the range of the query is much larger. So we took the maximum difference and kind of renormalize it. So this is the trick. Now, of course, I mean, why this number exactly here? So maybe there's something else. Will it work for the worst case scenario? Okay, so remember, and this is our domain knowledge. We said that the maximum depth per person is 10 million euro. So this is the maximum the bank will give one person. And now, differential privacy doesn't ask you like, on average, will you protect everybody's privacy, or maybe sometimes not? No, like pure epsilon differential privacy in any circumstances, any worst case scenario, the bound will hold. This will, let me just come back to make it really clear. This will hold for any neighboring data set, any worst case scenario. Okay, not like just on average. There are some different, some other variants of privacy on average, but this is like worst case scenario, which means in our case, what could be the worst case scenario is, for example, this we have, so everything is 0. People have no debt, so no money. And there is somebody who has like completely outlier, like the maximum debt the person can have, right? And of course, if you have neighboring data sets, one is if you have A, B, C, and A, B, C, D, you have to protect these neighboring data sets as well. So if this were, sorry, not D, excuse me, X, A, B, C, X. So this would be D, and this would be D prime. You have to protect these two neighboring data sets as well, because the presence of one person should have no influence, should have little influence or limited influence on the result of the query. So this is the worst case scenario. Okay, so we see that the maximum here that we can achieve, the difference of the query will be 10 million. And this is like domain knowledge. We have to know this. Okay, this is a publicly known information. It doesn't depend on the data set. It depends on our kind of, let's say, domain model or world model. Okay, we know this. So the minimum will be 0 and maximum will be 10 million. All right. So for this worst case scenario, I mean, we previously said like, okay, yeah, let's divide it by 2,800,000 something. And now we see that wouldn't be enough for this worst case scenario. So let's do it again. So ABCX is the full data set, and ABC is without the, okay, this will be the other way around. So this would be D, and this would be, how do I do that? D is all and D prime. Oh, that was correct. So yeah. So basically, here the true value, the true sum for full data set would be 10 million, because the total depth of my bank would be 10 million. And if I remove number X, Thunder, from the data set, the total depth will be 0. Okay, cool. So I'm gonna plug it here, and this has to hold. And again, I'm using 1 over epsilon, and then I just, well, previously we said like, well, it's gonna divide it. So I'm gonna divide it by this number, which we previously kind of identified. And now, well, okay, so this will exceed 1. Okay, this won't work. So how can we fix that easily? So exactly. I'm gonna plug in here 10 million. Now it will work not only for the other previous scenarios, but also for this worst case. Does it make sense? Any questions? You're kind of like suspicious? No? Okay. Yeah, so this is the easy trick. So we divided by the maximum difference of any two potential neighboring data set, even in the worst case, where we have everything is equal and there is one outlier, completely different. So this is an easy fix. And now we should finally somehow formalize this notion of the worst case differences. And this is the global L1 sensitivity. So we said that the max depth per person is 10 million. We saw that one person can change the sum query by the max value. And the max value was essential for scaling the Lepsius distribution. Okay, so this is important. This is why we define, so this definition of global L1 sensitivity. I'll explain L1 in a second. But basically, we have a function from a data set could be a number or could be a vector. Let's pretend it's a number now. So it doesn't matter. It's just a real number. So it's just a standard sum function or counting function, could be any. And then for any neighboring data sets, this is the difference of, this is the L1 norm. So this is the absolute value difference. Okay, so first question, what is L1? What do we mean by that? And maybe what is L2? So does it ring a bell? L1 or L1 norm? L2 norm? Okay. Euclidean norm? What is a Euclidean norm? Okay, no worries. What is the okay. So let's see. Let's say we have a x1 and x2 plane. And we have 2 points, and one is here and one is here. So what is the Euclidean distance between these 2 points? So let's say this is A and this is B. What is the Euclidean distance between these 2 points? Yeah, it's just the distance. This is like just the distance. And it comes from Pythagorean theorem in 2 dimensions. So, square root of squared plus squared. So Pythagorean theorem, I shouldn't explain Pythagorean theorem here, I guess. So this is the L2 Euclidean distance, Euclidean norm. What is the L1? What could be the L1? Have you heard of Manhattan distance? What is Manhattan distance? So, okay. Yeah, you need to relearn it. So it basically is would be the sum of the distances on each axis. And why is it called Manhattan distance? Because or taxi cab distance, because have you been to Manhattan before? New York? Okay, so New York is a grid, like avenues and streets. Every American city is a grid, okay? Most of them. Which means if you need to go from A to B, it doesn't matter if you go first, on the street and then the avenue or the street or something in between, the distance will be the same because you were just, you go by the squares and doesn't matter which one. That's why it's called taxi cab distance or Manhattan distance or L1 norm. It has a definition. So the L1 norm would be, or any P norm. So the P norm definition is if you have vector, if you have let's say, okay, so let's say X is in k-dimensional Euclidean, k-dimensional space, then P norm would be, if I'm not mistaken, xi, where I is from 1 to k, and this is, now this should be absolute value on P, and the whole thing would be to 1 over P, so like a square root. So if you substitute it with 1, you get just the absolute values summed up. If you substitute with 2, you get Euclidean distance, right? Check it for yourself. I mean, this should be correct. If you have like 3 dimensions, then it's the generalization of the Euclidean distance or Pythagorean theorem basically for 3 dimensions. Okay, so this is the norm L1. We're basically using L1 and L2 norm in differential privacy here. Okay. If you have just as I said, like if you have just a single dimensional space, so to say, then this will become an absolute value. And we saw the absolute value before. So it's just the difference of these 2 values. If this would be a vector, you subtract the vectors, so you get a distance between 2 vectors and just do the Manhattan distance. Any questions? Does it make sense? So you might have heard before, so you might want to refresh your knowledge of L1 and L2 norms. But it shouldn't be surprising. Basically, Euclidean distance is like the straight line between 2 points in Euclidean space, and Manhattan distance, like you take some sort of whatever gets you there. Fair enough. Okay. So this is global L1 sensitivity, okay? Why is it L1? Why is it not L2? It has something to do with the Laplace mechanism we're using. So for Laplace mechanism, we need to work with L1 distance for a reason, because of the triangle inequality. If you use wrong sensitivity, no, we'll still, okay, sorry, I'm too much fast forward. This L1 sensitivity will play a role in the normalization we just saw, because now for our example, the L1 sensitivity would be 10 million, because this is the maximum distance for any two neighboring data sets. So if FD was the sum of all the data, like 10 million, and FD prime would be 0, this would be the maximum kind of value, and we're going through all the different data sets. Okay, so the global L1 sensitivity for our example here, the global L1 sensitivity here is 10 million. The global L1 sensitivity here for this example is also 10 million, because this is our kind of domain knowledge. So we have to take this into account, because we cannot put the sensitivity just based on the actual database. As we just saw, if we use this, if we say, oh, the global sensitivity is 2.8 million, then on another database, which actually still fits the domain, it will break, as we saw. So we have to really think, from the perspective of the domain. So what are the constraints of our domain? What could be the range of the function we're asking? So for example, if the query would be, what is the sensitivity of what's the maximum age in the database? So the sensitivity of this query would be something like 0 to 120. I guess 120 would be the sensitivity of this query, right? Because physically, like in our world, people are, what's the oldest person on the world? 124. Okay, so you would say maybe 130, which means you would basically capture everything, like, all the possible values. Okay, in this case, the sensitivity will be 10 million because this is the domain knowledge. All right, so this is it. So this is the global sensitivity. And where are we? Here. And now, as I, just to stress, like for any possible neighboring data sets, right? This is important. Any possible neighboring data sets in our domain. There is a notion, so this is again repeating, global sensitivity is defined a priori by the domain, and it's a public information. So, if I ask you, okay, I'm going to ask you your Bang a query, so what's the max sensitivity? And you tell me, yeah, it's 10 million. Everybody can know that. I mean, there's no privacy involved in this, maximum sensitivity. And not depending on the actual data. If you want to make sensitivity depending on the actual data, there is something called smooth sensitivity or local sensitivity by Kobe Nissim, Adam Smith, and others from 2007. You might want to have a look into the paper. It's a little bit more tricky, kind of, and I don't think it's a thing that is actually used that much when you use differential privacy in NLP. So basically, you need to kind of know the global sensitivity to calibrate your noise. Okay. So what is the L1 sensitivity again doing? It captures the magnitude by which a single individual's data can change the function f in the worst case. Okay, cool. The worst case is here. So if we have this data set, okay, if we add one person, the influence on the sum query will be 10 billion in the worst case. And this is for the sum query, right? If we had some other query, like an average, we want to know the average, then you have to kind of compute your sensitivity for the average query, because for the average query it will be like 1 over n or something, okay? So it's always kind of, it takes into account the domain and the query you're asking. Okay, any questions? So this is it, global L1 sensitivity. Nice. Now, let's try to fix our example. So we have this worst case scenario, and instead of plugging, we plug in here the delta, the global sensitivity as a denominator. And since this will always be, less or equal than 1, because this will always, by definition of the L1 sensitivity, then be smaller than 1, then our proof of differential privacy for the sum query will work, and for any D and D prime in our data set. You can try by your own. But this is the worst case scenario. Like there is one outlier, which is the actual maximum value, and it's exactly the global sensitivity value. So this will turn into equality, but still it will be, it will hold, it will be protected. Okay? Make sense? Good. And now, well, we can make it actually nicer here because we just kind of hacked this Laplace distribution. So maybe we should do it more kind of formal. So now the correct scale of Laplace mechanism for any numeric queries is, so the, okay, let me just read what is here. Operator's observation, scale of the Laplace is proportional to the maximum difference of neighboring data sets, aka global sensitivity, lead us to the following. So if you tried hard, you would come up with this maybe after these examples, seeing, yeah, okay, so the scale is not 1 over epsilon, it's going to be the global sensitivity over epsilon, right? And it makes sense because the bigger one person can influence the output of the query, the brighter you have to make this Laplace distribution. And also, well, the tighter you want to have the privacy, this, the same, or I mean, reversely proportional. So, and now, okay, so you draw from this Laplace distribution, now the scale is correct, and you report, the value as before. So this is Laplace mechanism, and it's epsilon zero differential private. So, formal proof. So now basically what you see in a typical textbook is like, okay, this is Laplace mechanism and it's epsilon theorem. It's epsilon zero differential private, prove it. Like, okay. And it's a great exercise. But now we have all building blocks because we were talking about these inequalities over and over, and you know the PDF of Laplace by heart now, or you should know. So let's do the formal proof. But now basically we'll like reverse engineer what we kind of did as an example, reverse engineer to make sure that, oh yeah, if you do this in this way, that Laplace mechanism is actually differential private. And I'm proposing the following. So either you do homework or we'll do an exercise on that, like kind of whiteboard exercise. So let's do tomorrow an exercise on that, okay? So maybe not in person, maybe on Zoom. We'll decide later. But I would maybe we should go through this and to see the proof. I mean, now you should have all the building blocks, but who knows? Maybe it's important. I guess it's actually important too. Did you do any proofs, like formal proofs in like mathematical proofs? You did? You did? Okay. In which courses?
All of that, except for stochastic.
Okay. Okay. Mathematical courses. Yeah. Okay. Oh, you have to do proofs there. Okay. Everybody did proofs? Not much, maybe. I don't know. Yeah, a little bit. And okay. Yeah, so it's time to brush up the skills. Let's try. Okay. So now let me ask you a question. Okay. So what is the global sensitivity of the counting query? So what is counting query doing? We have Elise, Bob, Charlie, Alexander, and the bit would be 1, 1, 1, 1. What is the global sensitivity of counting query? So what is the maximum difference if you remove one person from the data set? 1. And now you see why we use a scale B1 over epsilon. Yeah, sure. Because the maximum difference on the counting query by removing one person is just 1. Okay. This is what we started. We said like, oh, okay, let's put 1 because it's convenient. Well, it's convenient because it makes sense because it's just removing one person and the difference is 1. But the general setup is, well, yeah, it's a numeric query, and there is something like global sensitivity. So for counting queries is 1 because you remove one person and it's just 1 plus or 1 minus. Okay, cool. What is for any sort of query? Well, you have to know the range of the query. So in our case, for the sum query, it would say, yeah, the difference would be 10 million because we just said so. For the average age would be 1 over 125, I guess, or 130, right? Because, so just do it for you. Okay, so mean query for age. And let's say age is somewhere between 0 and 130. Okay, so what is the global sensitivity? Not now, think about it, okay? It is something to do like, oh yeah, if you remove one person from the data set in the worst case, how the result will change. It has something to do with maybe the size of the data set, right? Because for mean, you need to know like how many people are in the data set, which should be public information. So if you have like n persons in the data set, and so on, do the math, okay? So this is the global L1 scale, L1 sensitivity. Any questions? If you screw up the sensitivity, everything will break. Like here. It didn't work because the sensitivity was wrong. And you might think, yeah, well, it's a stupid example, of course. I mean, I would never screw up global sensitivity. You'd be surprised because in some cases, some functions are kind of obscure and you might just, maybe forgot to multiply by 2 or whatever, some factor, and it happens, even like in scientific publications. Okay, so this is important to, to keep in mind, like the devil is in the detail. So now we have the Laplace mechanism, and we said like, oh, yes, let's just focus on real valued queries. So this will be just one value, but actually, you can output a vector, like multiple numbers at once. Why not? Actually, I didn't come up with any good example right now. What could be a numeric query? Maybe I'll have some later. I mean, one number makes sense. Like, what is the mean? What is the maximum value? What is the minimum value? What is the sum of things and stuff like that? Why would you need a vector? Like naively, I don't know. Maybe you want to ask for 2 attributes at once. So like, what is the mean age and what is the mean income? And give me just one vector. Okay, makes sense. I mean, you can either ask one query and the other query, or you can ask at once. It's the same basically. So the query will be in a, the output of the query will be some vector in k-dimensional space. And that's why we are using this, this L1 norm. So like Manhattan distance. So it's not a absolute value anymore. It's a Manhattan distance, but then everything will be the same. So for just single number, it's just an absolute value of the max difference. And for k, it must be the L1 norm. And we talk about this Manhattan distance, city block distance. So feel free to refresh again, but we just talked about it already. Okay. And how do you do the Laplace mechanism for multiple output or a vector output? Is that for each position of the output? So let's say we have a table with the same usual suspects, Elise, Bob, Charlie, and so on. And there will be age and there will be income. And we want to get let's say, an average. So this is the average, okay? Average age and average income. So then for each position, so we had k equals 2 here, to be precise. For each position, we need to know the global sensitivity. So correctly compute the global sensitivity. With multiple dimensions, it gets a little bit tricky. So you have to really be sure, like what could be, for example, here, the global sensitivity. It will grow with the number of dimensions because in each of the dimension, you're adding more. Like if you have just one dimension, you get like that. So this would be the maximum maybe. If you have 2 dimensions, you get like that and like that. If you have three dimensions, you get this, and maybe this, and you're summing things up. So each of the dimension, the maximum in one of these, maybe maximum age will influence the global sensitivity, then the maximum income will influence the sensitivity. And if there were like 3rd dimension, which would be debt in the bank, again, and then with more dimensions, you basically need to increase the sensitivity because you need to cover the worst case scenario. Like one person is basically here, one data set query will be here, and one data set output will be here. And you need to make sure that you cover, the distribution over these two will be, different by a factor of e to power epsilon. So this is getting tricky. Once you have the sensitivity, the global sensitivity, then for each dimension, you basically draw a Laplace distribution with a proper scale, delta over epsilon. And report this value. And what's important here? So right, I mean, what does it mean? Okay, so I is I1 would be for age, and I equals 2 would be for the income, and this would be like the vector. Okay, just to clarify. What it means, the random variables, or the draws for each of these dimensions are independent. Okay, so you first draw independently for one dimension, and then you draw independently for the other dimension. Okay, so there is no like they're independent. And again, the formal proof of this mechanism for multidimensional is very same as the previous one for just single value. And we should do it. You should do it. We can try to do that. And this independence is very important because it will play out in the without the independence, the formal proof would be, I don't know, impossible. It wouldn't. I don't know. Maybe it wouldn't work at all. So it's important that this independence is in there. What does it also mean? Is that, and I'm getting like a little bit ahead of time, but basically it means you can ask two queries after each other, like one query about one dimension and another query about the other dimension, and they are independent random kind of draws, and you just need to sum up the privacy budget. So you need to split the budget between these two. Okay, this is interesting, but we'll come to that later. Okay, so this is a multidimensional Laplace mechanism. Okay, everybody should, it's like basic really mechanism in differential privacy, pure differential privacy. Any questions? So can you try to do the proof? We should try. You should try. I did it for myself back in the days. Yeah. You learn things that you think you knew, but then it's like, no, not really. Anyway, let's move on. Okay, so far, let me just step back a little bit and think about what we did so far. So we are far away from NLP still, in a way, but it's great because we're building the basic building blocks of privacy. So we started with, whatever you try to do without any randomization will just break. Linkage attacks will just, it's your enemy, whatever. So then we said like, okay, we need to add some randomness. And one notion of randomness or protecting everybody's privacy is the notion of neighboring data sets. So basically you make it whether or not you are in the database will be to some extent indistinguishable from the scenario where you are in the database. So these will be similar. So, and since this is probabilistic, then I can only get some guarantees of privacy or probability leakage of your information. So this is the same thing. I mean, I'm the bad guy and the good guy at the same time because I ask the query of the database and I get something which is random. There will be some error. We didn't talk about errors and accuracy so far, but I ask you to compute the accuracy of the on the Laplace, like if you're how's likely that you're one standard deviation from the mean of Laplace. So you should try. It's like a one integral. And we had it for numeric queries. So we are talking about like a counting query. It's just basically how many people are in the database with this bit. Now we talk about like sum queries. So how many summing up things. We talk about maybe mean queries. So what's the average? So basically, it's just these are just numbers. And numbers kind of play well with this Laplace distribution because this Laplace distribution is actually doing what we want, basically saying, well, the bounds are exponential, right? I mean, we don't multiply by a number. We multiply these probabilities by e to this exponent, the e to this far epsilon. So, and that's why this Laplace is a very nice distribution to model this. And now, maybe we don't want to report a number. We want to ask, query the database about something else, which is not a number, but still we want to make it private. So I was thinking about the example because the original example, so it's called exponential mechanism. We'll go to that. The original examples are still numeric and they have even like less to do with NLP. So exponential mechanism is actually used in NLP already. So once we finish that, maybe we'll show some examples next time. But I want you to understand what this mechanism is doing and why it's important. And I came up with my own kind of example, which I didn't see in any existing textbooks, because the existing textbooks were about bidding and auctions, which is kind of, I don't know, maybe interesting, but I'll try something else to make it more visually understandable. So let me try to motivate this thing. So we have a secret. Okay, so maybe it's completely, completely nonsense, but maybe it makes sense. So we have a secret society where we have four people, and we know there are 4 people. So it's a public information. So there's 4 people in the secret society. Maybe we know who is in there, but we don't know where they live. We don't know the addresses, the cities of Elise, Bob, Charlie, and Sander. We don't know where they live. So this is a secret thing about them, okay? And let's say, and they don't know of each other where they live, okay? So they shouldn't know anything about them because this is a secret society because of the privacy or whatever. Maybe they have some, I don't know, some stash of money or something like that. And they want to make a meeting, and they want to meet in the middle. So they want to pick a city where the next meeting should take place, and it should be in the middle. So not, they have to just, can drive a car maybe. So middle, in terms of like GPS coordinates, okay? And there is somebody who they trust, maybe they trust you. So, you will ask them, okay, so where do you live? And then you want to say, okay, your next meeting will take place in this city because it's just in the middle of everybody. But they don't know, they cannot know from each other where they live. And we have also like limited range of cities. So we have Los Angeles, New York, Washington, Toronto, and there may be others like Ottawa, Memphis, La Habana, which is, where is that? This is Cuba? Yeah, I think it's Cuba. So we have US, Canada, and Cuba. So sounds a little bit realistic. I don't know, maybe it's a little bit realistic. I mean, I can kind of imagine this scenario. So you're gonna ask them, okay, where do you live? And then you will tell everybody, okay, so next meeting will be there. Okay, so here's the map again. So we have, okay, what do we have? So we have Los Angeles, New York, Washington, Toronto. So we have Ellie's here, Los Angeles, Washington, New York, and Toronto. Okay, so, and then we should find like a mean vector of the GPS coordinates, right? So the centroid basically of this cluster. So I don't know, where should it be? Somewhere between, I mean, these 3, I don't know, maybe somewhere like, let's try here. This could be the mean, roughly, maybe. Okay, and they should meet there. So you're gonna report back to them like, okay, so we're gonna meet here, and I don't know which state this is. Okay, who knows the US? Like, what's the state of the US? It might be Tennessee, but I have no idea. Can somebody look it up? I'm just curious because I forgot. I had this map open like some time ago, but there might be a state of the US. Arkansas. Okay. Okay, so Arkansas. So maybe Tennessee. What's up there? Is it Tennessee here? Missouri. Okay, so my US geography is really bad. Anyway, I know the West and the East. And now they're gonna ask you, okay, so where are we gonna meet? And you say, okay, we're gonna meet in Arkansas here in the city. No, actually, no, we have a list of all cities. So I think the closest here would be actually Memphis. Can you check where Memphis is on the map? It's somewhere around here, I guess. The next here? Here? Okay, somewhere here. So there's Memphis. And you're gonna say, okay, it's Memphis. Now, the 3 guys from the East Coast, they collude with each other and say they kind of reveal the information to each other. So what is on the East Coast? So Bob, Charlie, and Sander, New York, Washington, Toronto, they tell each other, oh, I live in New York, I live in Washington, I live in Toronto. Let's find out where Elise lives. And if you tell them just the mean, well, it's pretty clear that she's not living in Ottawa. right? Because if she were in Ottawa, like the mean would be here, and the city would be either Toronto, New York, Washington, or Ottawa. Maybe it's pretty clear she doesn't live in La Habana because you tell them Memphis and you didn't tell them Washington, which would be like the closest city here if you take the mean. So, and she also doesn't live in, maybe she lives in Memphis. I mean, you can do some math, you can just find the most likely kind of explanation of that. So these guys would kind of find out, okay, she has to be somewhere on the West Coast. And it's a good clue. I mean, it's now they're learning some information, so they can basically, well, there's only one city left, right? It's Los Angeles. Yeah, okay, so not good. So just reporting the average, as we saw many times before, it will break privacy. So we want to do this private. I mean, let's do it more concretely. So I actually looked up the GPS coordinates of these cities. So we have latitude and longitude, and we call this database D. And the mean of this database of the secret society was Memphis. So this is the true coordinates plus minus 1, and the closest city was Memphis here in the middle. Okay, so here's the Memphis in Tennessee, and Arkansas and Missouri. Okay, thanks for the hint. Okay, we learned something today. And this is kind of yeah, this will break their privacy. So even though they trust you, you didn't provide anything on top of that. Okay. Is it kind of like a realistic scenario to some extent? Well, maybe not, maybe yes, but it demonstrates that we need to protect privacy in this case. Can we protect privacy in this case? That's a question. And maybe we can. The thing is, now we don't have, we want to basically, the function is that I want to report a discrete item from a set of cities. So I'm not, you're gonna tell me a city, like from all these cities. So what do we have? Ottawa, Toronto, New York, Washington, Memphis, Los Angeles, La Habana. I'm gonna ask you, where should we meet? And you have to tell me one of these cities. It's a little bit different than like, tell me a number, how many people are in the database, or, it's like a discrete kind of thing. So you have to report back a discrete value. Okay, so maybe the Laplace distribution is not, how can you model this with Laplace distribution? Maybe somehow like projecting this into something, but yeah, there is a better alternative, which in turns, this better alternative is a generalization of the Laplace distribution as the Laplace mechanism, as you will see later. But anyway, so we wanna measure something as well. Okay, so this is important. Now we're gonna call it the utility function. And we're gonna the utility function is gonna use some sort of Euclidean distance of the database. So in this case, Euclidean doesn't have to do anything with the L1 norm or L2 norm we talked before. This is now just to measure what is distance between Memphis and Washington. Okay, so, and because we are in 2 coordinates, it's gonna be Euclidean distance. We can use some better distance, which would be more, I don't know, like more, because the states are big and it's like hemisphere, so there could be better distances than just subtracting GPS and using things. We're gonna ignore it and we just say, okay, it's gonna be, the direct distance on the GPS coordinates. Okay. So we wanna measure distance between cities, and we wanna measure the distance between the mean of the database. So okay, what is the center rate of the database and any city we have in our inventory. And we're gonna call it just D because it's distance, and this is the database, and this is a city, which is one of those 6 or 7. And of course, this distance is the smaller, the closer, so the answer would be better. I mean, of course, we want some utility. I mean, we wanna meet really somewhere in the middle. I mean, you can tell like, okay, everybody meet in La Habana, but then everybody has to kind of, spend a lot of money flying there. So it's better to meet in the middle. Actually, this example makes sense. When I'm thinking about it, why not? So this is good. I mean, this utility function is great, but we're gonna make a little bit turn, and we wanna make the utility higher for closer cities, right? So we just basically turn it around. So for any cities which are just close to each other, the utility is high because this is the true answer is closer to the mean, or sorry, the city is closer to the actual mean, so it has a high utility for everybody. Everybody will be happy more just, to travel in the middle. And of course, if I say the utility, let me just come back. If we travel here, so the utility will be smaller, and then the utility will be high if everybody has to kind of travel some far away, So the far cities, the utility will be smaller because the distance is higher. So we just flip the fraction here, basically. So I'm gonna call it U, and again, it's gonna take the database and the city C. Okay, so 1 over D. And I'm gonna ignore the 0 in the denominator for simplicity. So if the mean is exactly fitting one city, it will turn out to be 0 distance and it will break, but actually we can fix it like that. Why not? Now it won't break in any case. Okay, this is fine. This is what we define. Utility function is up to us to define. Our utility is, the closer to the true mean, the better, because then I can guarantee that everybody will kind of travel cheaper in our secret society. We're like poor secret society. Okay, so maybe they have to walk. I don't know. Okay, so this is the utility. Everybody agrees? Distance makes sense here. So, and our query should, of course, return the element with the highest utility. The highest utility will be the true mean, right? But as we saw, like the true mean is kind of unprotected, so maybe you want to do something about it. So our query is gonna take the database D, compute the mean coordinates, and choose city with the highest utility. Okay, so this is basically the same problem as we had before, but now we included the utility in there, which was gonna help us to kind of make decisions about things. Because what happens for neighboring data set D prime? And yeah, we saw it before. If we have two neighboring data sets, by including or removing at least maybe, so the difference, there will be some difference. And now we talk about the global sensitivity today in the Laplace mechanism, and in this case, we need to see like what is the influence of one person on the utility, okay, or the output of the query, so to say. Excuse me, on the output of the query. So okay, so does our utility function have sensitivity? Yes, it does. And it's very similar to this global sensitivity we had for just for the numerical queries. But now, because our utility, well, okay, let's do it formally. So having a database X and the range, which is just some things. In our case, the range are the cities, a set of cities. It's discrete. It could be continuous, but it will make some things harder maybe to compute. So we just take a discrete. So any combination of city and a database will give us a score. Okay, so this is what we had. Like we take the database, its mean, and a city, and it will compute 1 over the distance. This is the utility. So we can do it for all the cities we have in our vocabulary, so to say, and it will work. Now we define the sensitivity. I don't want to motivate the sensitivity again because we did motivate it for the other cases. So I'm gonna just here spit out the definition, but it's very similar. So we take the maximum difference of the utility for any neighboring data sets D and D prime, and also for any item from the output. So in our case, for any city in our list of all cities. So anything I want to output from my function with any pair of neighboring data sets will determine me how big a influence of one person in the data set will be on the utility function. Does that make sense? Why? Yeah, because I want to care, I need to care about outliers. This is what matters, because the bigger the outlier is, the bigger the difference will be between a set of 3 people and 4 people, because the utility will be, and maybe for this city, okay, maybe let's pick the city. This will be C. So the utility for picking C for this data set is much different than the utility for picking this city for the full data set. And we need to take care this kind of outliers into account. And I like this example actually for the outliers, because you see these are actually outliers, and you need to protect everybody. You need to protect not just these guys like hiding in the crowd. You need to protect everybody who's living like on the very edge of the world. So for any pair of neighboring data sets and any potential C, so it could be this one, could be this one. No, we didn't have this one. We had La Habana, so this one, and we had Ottawa. So for all of them and for all combinations of neighboring data sets, you need to find out what is the maximum impact of one person extra in the data set. Because this will help us to scale some probabilities, as we will see. Okay. So, okay, so we have this utility for this exponential mechanism. So again, it's for all potential outputs, the maximum distance for any neighboring data sets. Okay. And now you see why it's better to have a discrete kind of output, because if you had some continuous things, you need to kind of really do some math, or there'll be some, I don't know, maybe some integrals or some optimization things. Yeah, so if you have discrete things, you can compute them. Like finite sets are the friend here, which is great. Okay, so how to choose now the city privately? So what do we have? I mean, you know the true value, you know the true mean. Now we know the global sensitivity as well. And what we wanted is to take the database, compute the mean coordinates, and choose a city with the highest utility. But we want to do somehow be differential private, which means for anything we're going to output, the difference for these two databases, either one and one without one person, will be bounded again by privacy budget. So this is the definition of differential privacy again, and we want to make it work for our case of outputting like discrete value. So we need to sample C somehow randomly. Somehow. What is the worst? What could be like the most kind of simplest ways of protecting privacy of everybody? How would you pick a C? So let's say, come back to this example. Oops. Come back to this example. So again, I have LA, Toronto, Washington, New York. And I'm going to ask you, where should we meet? And I want you to protect privacy. What you going to answer? Just without thinking. What you going to do? You can make a decision based on people in there, but then you have to be very careful. What could be the... Pick any random thing. Exactly. If you pick any value randomly, you will protect privacy because your selection doesn't depend on anything in the database. It's the same as picking a random value in your age. Like, what is the average age in my database? And you say, like, I don't care what's in the database, just pick random number between 0 and 130. Yeah, that's great. It will protect everybody's privacy perfectly. What is the utility of that? Nonsense, because I didn't learn anything. What is the utility of picking random city here? Trashy, because everybody will be just, have to kind of take a long flight. By chance, you might be somewhere close, but most likely you won't. I mean, this is a simple example, so it's maybe okay, just randomly pick one. But maybe it's a bad idea. So this is the easiest way of just pick randomly. So yeah, good for privacy, not for utility. So we have to do something better. So, and any other idea? So we have the utility, we have global sensitivity, which is the maximum value, and we need to have this kind of thing in place. So we're gonna, now without much more explanation, I'm just gonna, say how the exponential mechanism looks like, and we're gonna, dissect it a little bit to understand what it really means. So this is the exponential mechanism. So basically, I'm gonna put a probability distribution over my range. So I have these cities, right? I have a, what was that? Okay, we have the cities. So we have Washington, we have New York, we have Ottawa, we have Toronto, we have La Habana, we have LA, and what was Memphis, okay? These were the cities. And I want to, if I said like completely randomly, I would basically say 1, 2, 3, 4, 5, 6, 7. So I would say the probability of sampling of each of them would be 1/7, okay? Uniform. No, that's a bad idea because there's no, utility is bad. So I'm gonna say, I want to add some probability here, which is proportional to the utility, right? Because I want to pick numbers which have, utility. So the naive solution would be, okay, what is the given the database, what is the utility of Washington? So I would just say utility of the D and this city, and here the utility of D and the city. So it will give me some number. These numbers are unnormalized, so I would need to normalize them. So this explains this normalization. This could be like a good idea, but now we're missing the exponentiation. So what we're gonna say, yeah, let's put everything through exponentiation, right? Because we want our privacy protection to be, e to epsilon, not just epsilon. So we're getting somewhere closer here to this form, okay? I mean, just you can ignore this for now, but just look at this nominator. And of course, so I'm plugging here. So we had the utility and the exponentiation. Now we want this privacy budget to play a role. We want to control the strength of the privacy. And what we do is just basically multiply this utility by this privacy budget, right? Okay. And as we saw before, again, we need to take into account the utility, the global sensitivity of this utility function. So this is the delta. And in this case, this is going to be 2 deltas, because with 1 delta, the proof will fail. So you need to have 2 deltas. So this is how you, basically assign a probability distribution for each of the cities here. And if you do just the denominator, it will be unnormalized. So you just need to sum up and divide. And this is exactly what this is doing, right? So this is the denominator, like the raw values, and then just you sum them up and divide the whole thing to get a true probability distribution, which will sum up to 1. Make sense? Okay, now we dissected it, like what it means. And we understand also like why this utility is here, because this is proportional to the utility. We want to the higher the utility, the higher the probability, right? Cool. The higher the epsilon, the higher the probability. This is interesting because epsilon, yeah. What happens if you have smaller epsilons? Well, if epsilon goes down, this distribution goes more uniform. If epsilon is large, then the maximum value will get much larger. Does it make sense? No? Yeah. With large epsilons, the distribution will get more spiky, which means there will be less privacy, of course, because then you have chances more sampling, the true value than the other values. Yeah. And the rest is just normalization and scale. Okay. Cool. So I would say, as a homework, try to implement this example in NumPy. I just, I didn't manage to finish everything, but it's just you see, like you have the cities and this GPS coordinates, and just try to kind of make this secret society meeting happen, and just try to run it and ask, okay, where should we where should we meet next? Get the answer, and then you'll see, okay, yeah, it makes sense because it's random. So you basically should be able to see this distribution for each of the cities, and then play around with the epsilon to see, how it kind of, changing the distribution or proportion in the distribution. And as an exercise, so this is the 3rd exercise today. Actually, I prepared maybe too much for the next exercise, but we can stretch it into 2 exercises. We need to prove that this is actually differential private. It will be a little bit similar to the proof of Laplace distribution, but there's some other tricks in there, so we can, we can try to go through that. So this will be like another thing that, can you trust me? No. When I show you the proof, then yes. No. And you can, and the thing is, your secret society, no, I mean, you're the proxy for the secret society. So you can show the secret society everything you know. What is the global sensitivity? Sure. What are all the cities? Yeah, sure. What is your mechanism? This is it. This is public information. You can show them the proof. So everything is public, nothing is hidden. The only thing is that, yeah, you will make a random choice. Like when you ask them and have the true answer, you will compute the probability distribution, and then you toss a coin, or no, not I mean, coin tossing is a bad example here, but you run a very cryptographically secure random number generator, and you will then pick one from this distribution, and it will be something. More likely it will be something with high utility than something with low utility, but then you will tell it to me. And everybody will know that, and nobody, even like if these three guys just go together, the privacy of, let me come back. We have these Elise, Bob, Charlie, and so these three guys, if they get together and collude against Elise, the chances that we will release information about Elise will be bounded by this. Yeah. How large the epsilon should be? Well, depending on how, depending on the utility they want to achieve, or depending on the privacy strength. And again, this is a trade-off. So you have to trade one for the other. Okay, so this brings us to the, oops, now it froze. Brings us to the end of this, now it crashed completely. End of this lecture. Any questions? Okay, so let me stop recording and then we'll discuss the exercises.